right. Hi everybody. Let's start. As a reminder, please turn on your video if you can. If not, that's also fine. And so let me first remind you what we did last time. Well, last time I was talking about some properties and examples of cluster algebras, and so basically the three properties were, that's properties of cluster algebras, which I haven't defined yet. So the first property is the Laurent phenomenon, right? Which in particular implies that if you plug in things equal to 1, then you get positive integers. Well, you get integers, and so the second property was periodicity, which we saw only for the frieze patterns, and the third one was positivity, which meant that the coefficients of these Laurent polynomials were positive integers. And so let me mention that the first and the third properties are going to be always true. So for all cluster algebras, this is always going to be the case. And this periodicity is sometimes going to be true and sometimes not. Usually not, but I'll tell you exactly sort of when it's true. So let me write sometimes here. And let me also mention, last time I created a little confusion about these coefficients of Laurent polynomials, so let me try to do this more carefully. Let me say that that's the usual definition. The Laurent polynomial ring is usually denoted like this. It's C or R or Z adjoined with x1 to the plus or minus 1, x2 to the plus or minus 1, and etc. xm to the plus or minus 1. And so it's basically polynomials in xi and xi inverse. And so in particular, when I'm talking about so let's say I have some Laurent polynomials, x1 squared over x2, 5 times this plus 2/3 times x1, I don't know, x1, x2 divided by x3 squared, or something like this. If this is my polynomial, then these are the coefficients. Right. As opposed to having a ratio of a polynomial divided by a monomial, and then you're going to talk about coefficients of the denominator. So none of that. When I'm talking about coefficients, I'm talking about these things, coefficients of a polynomial in xi's and xi's inverse. And so in particular, when I say that the coefficients of my Laurent polynomials are positive integers, then that actually means that that's kind of a stronger property. So the denominator has coefficient 1, basically. And let me also remind you what were the examples. Well, so far there was only 2 examples. The first one is the summus for sequence, which is defined by a recurrence relation like this: xn plus 1, xn plus 3, plus xn plus 2 squared over over xn. And there was also, so that's the first example, and the second one was frieze patterns, where the condition was that they are some arrays of integers, and then for any diamond like this, the condition was that this is the SL2 condition, AD minus BC is equal to 1. Right, and so in the first case, here the the cluster variables were just the initial conditions, x0, x1, x2, x3, and here the cluster variables were any kind of, you have a row of ones, and then you have another row of ones at the bottom, and then you choose some lattice path from top to bottom, and then these things, the entries on this lattice path are basically these are your cluster variables. And okay, so any questions about what I did last time? Okay. Now let me, if there is no questions, let me try to do some combinatorics for a change. And well, still about frieze patterns, but let me ask you the following question. Right, so, oops, okay. Question that I have is, how many positive integer frieze patterns of order n there are? So let me remind you, do I have a, yeah, so here's a picture again. Right, so this is a typical frieze pattern of order 7, and well, you can see all entries are integers, right? And we have this SL2 condition for every diamond. So how many, let's say I fixed the number of rows, I fixed some number, let's say 7, and then I'm talking about 6 rows. So how many such pictures can I produce? Is it going to be finite or infinite? Anybody have a guess? Right, yeah, that's a great guess, right? For any, if I choose any kind of cluster like this, there is a power of 2 of such clusters, and each of them is going to give me a different frieze pattern, hopefully. So a guess is, a possible guess is 2 to the whatever n minus 1 or something like this. Any other versions? Okay. Yeah, let's try to compute some examples. Let's say I choose n to be equal to 4, right? So I have wait, should n, yeah, I have 3 rows. So 1, 1, 1, 1, 1, and then this is also going to be 1, 1, 1, 1, 1, and then if I start, wait, is this too much? Yeah, let's do, I'm supposed to have 3 rows, so okay, not good. 1, 1, 1, 1, 1, and now here if I have a, this is going to be 2 over a, and then this is going to be a again, 2 over a, and etc. So as you see, it's periodic because it's always periodic, and so the positive integer solutions are only a is equal to either 1 or 2. So that's a power of 2. Maybe not 2 to the n minus 1, but yeah, so basically I either choose a cluster that goes sort of like this, or it goes like this. Anyways. Right, yeah, let's consider these to be different. Right? So I do not consider them modular shift, even though Yeah, let's just choose. Let's circle some entry, and then yeah, let's just pin the pattern to the plane. Just each of them. Let's fix some x-axis and the y-axis, and so each entry has a coordinate in the plane that's fixed. Anyway, so the answer. So the answer in this case, there is, so when n is equal to 4, there is 2 frieze patterns. Okay, let's do n equals to 5. When n is equal to 5, I'm supposed to have 4 rows. 1, 1, 1, 1, 1, 1, 1, and now it's going to be 1, 1, 1, 1, 1, 1, 1. And I did this example last time, so basically you start with like a and b, and then here you have b plus 1 over a. Here you have a plus b plus 1 over ab, I think. And then here you, surprisingly, there is a cancellation going on, and then you get a plus 1 over b, I think. And then you have a and b, right? And so the triangle, I had these, I was drawing these triangles, so this triangle here is going to be the same as this triangle here. Just, it's a glide reflection. So okay, now here's a question: how many how many pairs a and b are there such that all of these things are integers? Let's make a table. So integer solutions. Let's say a and b. So for example, like 1, 1 is an integer solution, right? Can you give me some other ones? Oh, okay, great. 1, 2, and 2, 1. Right, if one of them is 2, then yeah, this is going to be always 1 plus 2 plus 1 is 4, and this is going to be 2. Yeah, so these are all integers. Any other? Okay, 3, 2. Is that it? Okay, it's symmetric, so 2, 3. Yes. Anything else? Yeah. Yeah. Okay. Right. So is that it, or should I keep going? Yeah. Yes. Right. Positive. Is that it? All right. Hmm? Okay. So no more. Are you sure? Yeah. Okay. That's actually that's correct. So the answer is that for n equals to 5, there is 5 frieze patterns. 5 integer, well, positive integer frieze patterns. Z plus frieze patterns. Oops. Okay. Now do you have a guess? What is going to be the answer for general n? It is not a power of 2, as you can clearly see. There is a 5 in here. So what is the... Oh, okay. So another guess is that there is Catalan many frieze patterns. And so let me remind you that the Catalan number is, let's say Cm is 1 over m plus 1, 2m, choose m, and Cm is the number of triangulations of an, I think, m plus 2 gon. Right, so if n is equal to 5, then I can choose like a 5 gon. No. Well, right, so if I choose these clusters, then I'm only going to get a power of 2 variables, right? Because when I always choose like a step down left or down right. But then, so in particular, this computation, here we just computed all possible integer solutions such that all of these entries are integers, right? So in particular, I think one of them is supposed to not come from a choice of an integer cluster. Is that right? Or maybe, yeah. Anyways, there's going to be some examples where there is no cluster of all ones in this frieze pattern. Can I? But I think that yeah. Let me give you an example where there is no cluster of ones. But I have to go. I think I have to take n equals to 6. If I put 1, 1, 1, 1, 1, 1, 1, and then I can choose 1, 3, 1, 3, 1, 3, etc. This is going to be 2, 2, 2, 2, 2. Hopefully this works. 3, 1, 3, 1. Is that an SL2 frieze pattern, right? Right, so this is, so here there is no cluster of ones. You cannot draw a lattice path from top to bottom that would consist only of ones. And yet somehow it's an integer frieze pattern. Yeah, anyway, let me try to draw 5 possible triangulations, just to remind you about Catalan numbers, and then I'm going to state a theorem. Yeah, so 5 triangulations look like this. All right, good. Yeah, okay, so here's a theorem. Here's a theorem. The number of positive integer frieze patterns of order n is Catalan is equal to the number of triangulations of an n-gon. So yeah, this is not a coincidence. This 5 is equal to this 5, and so for the hexagon there's going to be like 14 integer frieze patterns, and etc. And yeah, so this number is what I would denote Cn minus 2 because of this kind of shift by 2. Yeah. Okay, and so so one positive integer is equal to another positive integer. In combinatorics, we ask if there is a bijection between these two sets of objects. So the question is there a bijection? Do you have any idea how to go from here, from something like this to something like this? That's actually a pretty good That's an almost correct guess. Yeah. So, I mean, it's a little tricky because there is like n squared. If I choose a triangle, then there's going to be n choose 2 non-trivial integers. So it's and there's only n degrees, but yeah. Let me try to give you a construction. So the answer is yes. And so I'm only going to describe the construction, and then it's going to be an exercise, which may or may not be hard. So yeah, let me just try to describe the construction. So let's say you take an n-gon, and then you choose some triangulation, and you label your vertices in some fixed way, like 1, 2, 3, 4, 5, 6, or yeah, you just choose some order on the vertices, well, the cyclic order, and then you record for each vertex. You record the number of triangles containing this vertex. So, for example, here I'm going to have 1 triangle, 3 triangles, 1 triangle, 3, 1, 3. And then what do I do with these numbers? If I want to get something like this, well, I'm just going to put them in the second row of my frieze pattern, because the first row is going to be all ones. Put them in the second row of a frieze pattern. And then once you do that, you can recover all the other entries just using the SL2 condition. SL2 condition. So if I start with this guy here, then yes, I put 1, 1, 1, 1, 1. And then 1, 3, 1, 3, 1, 3. So I kind of write them down periodically. Once I write 6 numbers, and then I just repeat, because as we know, frieze patterns are periodic. And then the SL2 condition tells me that here I'm supposed to have 1 times 3 minus 1 times x should be equal to 1. So this is going to be 2. So these are all going to be 2. And then if I apply the SL2 condition again, then 2 times 2 minus 3 times x is going to be equal to 1. So surprisingly, again, I'm dividing, but surprisingly, if my second row comes from a triangulation, then the remaining entries are going to be all integers. And then 1, 1, 1, 1, 1. Just the last row is going to be also uniquely determined, and after n steps, I'm going to get all ones. So that these are all kind of exercises for you to check. So theorem is that this construction gives the desired bijection. Yep. And the proof is an exercise for you. Which, by the way, yeah, so there's going to be homework, because we have a book, and the book has exercises, so I'm going to give you homework problems, but then you're always allowed to replace any homework problem with an exercise from class. If you would like to, if you found some exercise that you find interesting, then you can always kind of choose to do that instead of the boring homework I give. Okay. Any questions? so far. The lectures are recorded. I'm recording right now, yeah. But you can also write them down if you would like, because I mean it's yeah. By the way, so, right, yeah, yeah. Whoever asked the question was quiet right now, so please crank up your volume. But yeah, so by the way, somebody told me last lecture that I'm supposed to repeat the questions, which I didn't, so I had to add subtitles to the YouTube video, and that took a lot of time. So please remind me to repeat your questions when you ask me. Okay. Any other questions? All right. Now let me try to slowly move from frieze patterns to some something more, let's say, something less recreational. And well, so far it's still going to be pretty high school level, and but yeah. So the general title of what I'm gonna do next is called Examples from Total Positivity, which some of you may know about and some may not know about, but it's fine. So in this class I'm not going to discuss total positivity too much, but it is always closely related to cluster algebras. They kind of go hand in hand, but I'm going to focus on cluster algebras. Anyways, let me try to remind you of something from high school. Right? So this is called the Ptolemy theorem, which is that, let's say you have a circle, and then you choose some 4 points on the circle. Let's say A, B, C, D. It works. A, B, C, D. And then you draw the diagonals. And then there is the Ptolemy's theorem is a certain relation between the length of this quadrilateral and the diagonals. So can somebody tell me what it's going to be? Nice, thank you. Yeah, that is correct. This side times this side plus this side times this side is equal to this diagonal times this diagonal equals. Wow, yeah, that is pretty impressive still. AC times BD. Yes, I haven't been to high school in quite a while, so I had to look it up actually. But yeah, so this is true, right? There's this relation for an inscribed quadrilateral. And so, okay, here's what I'm gonna do now is I'm gonna choose, instead of choosing just 4 points on a circle, I'm gonna choose n points on a circle. Right, let's say, like, I don't know, A1, A2, all the way up to AN. And then I'm gonna study the distances between these points. So let's say Pij is just gonna be the distance between AI and AJ. Right, for I and J between 1 and N. So this is symmetric if I swap I and J. And yeah, so then the condition on these Pij's is that for all A less than B less than C less than T, I have this Ptolemy's theorem tells me that PAC times PBD is equal to PAB times PCD plus PAD times PBC. And so in particular, if I choose a, well, so question is, how do I'm going to want to choose some of the p's. Let's say I know some of them and I want to compute all the others. So somehow these are algebraic relations between these different variables. So I want to choose a certain cluster of p's so that I can compute the rest uniquely from that. And any idea how do I do that? Yeah, yes, yeah. Yes, yes. A1, A2, all the way up to AN. Yeah, thanks. Okay, so any guess how do I, so how many of these things do I have to, you're allowed to choose any diagonals you want, but then the condition is that you should be able to compute the remaining diagonals uniquely. All right, let me tell you the, well, one possible solution, which is that I'm going to say that a collection of Pij's, a collection of diagonals, these form a cluster if the corresponding diagonals, let's say AI, AJ, form a triangulation of my n-gon. Right. So I have an inscribed n-gon, and then I choose, let's say 1, 2, 3, 4, 5. So I choose kind of, yeah, let's say I'm also, I choose P13 and P35, and then I also choose P15, P12, P23, P34, and P45. Right. So, okay. Question is how to compute the remaining. So let's say I know all of these Pij's. How do I compute the remaining ones? Yeah, okay, that is true, right? So if I only fix P12, P23, and etc., then they uniquely determine the inscribed n-gon, so I'm already, in principle, supposed to be able to compute the rest, right? But then, yeah, maybe in 10 minutes from now, I'm gonna leave the world of planar geometry, and then it's no longer gonna be true. So this relation is gonna stay, but the other kind of secret relations that come from planar geometry are not going to be true. So yeah, so okay, my actual question is how do I compute the remaining Pij's using this relation here? Yeah, thank you. Yeah, that is correct. So let me introduce an operation. Usually it's called a flip of a triangulation. A flip of a triangulation triangulation consists also, oh, please remind me to do this as well. A flip of a triangulation consists of choosing a quadrilateral and then flipping one diagonal. Well, and then let's say replacing one diagonal with the other, and replacing one diagonal with the other one. So in other words, if I choose some diagonal, it's always going to be adjacent to two triangles, one on the left and one on the right. So it's going to be contained in a quadrilateral, and then if I erase this diagonal, then there is only one other diagonal I can put in to preserve the triangulation condition. I don't know if that's clear. So a flip goes like this. You have a quadrilateral inside a bigger triangulation, and then it's triangulated like this, and then you replace this diagonal with this one. And so I guess should I yeah, I should introduce some more notation. But yeah, anyways, the claim is that any two triangulations are connected by a sequence of flips. So for example, did I have a picture? Right. For example, I have 5 triangulations here. They are all right. You can take this triangle. Wait, did I not? Okay, I'm supposed to rearrange these. So from this triangulation, I can go to, let's say, this one. Yeah, let me do it like this. And then from here, I can go to, which one? This one, I think. And then from here, I can go to this one, and then this one. And so together, they kind of form another pentagon. And so, by the way, this graph, right, you can take all triangulations and then you connect them by, you make a graph where the vertices are triangulations and the edges are whenever I can perform a flip from one triangulation to the other. And then this graph is called the associahedron. Well, it turns out to be the edge graph of a convex polytope. And this polytope is called the associahedron. But anyway, I'm gonna discuss this later. It's also related to cluster algebras. Yeah, all these kind of Catalan objects showing up and the associahedron, they all can be nicely explained by cluster algebras, as I'm gonna do later. But okay, so far let me use this claim, right? Any two triangulations are connected by a sequence of flips, and therefore corollary any Pij is expressed, well, actually uniquely, but well, yeah, anyways, is expressed in terms of Pij's, well, in terms of a cluster. Let me just say that. right? So you start with the cluster, which is a triangulation, then you kind of apply these flips until your desired diagonal belongs to the triangulation, and then because you apply this relation here, right? This relation allows you, if you know the sides of a quadrilateral and you know one of the diagonals, then the other one can be obtained by dividing by this guy. Yeah. Okay, so let me now try to establish the terminology. This terminology is going to be kind of the same for all cluster algebras. And so before I was kind of pretty vague about like whether what belongs to the do the sides of the polygon belong to the cluster or only the diagonals. So let me try to make this all precise and clear. So a cluster, by a cluster, I'm only going to mean a collection of diagonals that form a triangulation. And let me say that the sides are, because the sides, they belong to any triangulation, right? And I'm never going to divide by the side. And these are usually called frozen variables. Frozen variables. Sides of the polygon. And if I take them together, this is called the extended cluster. Right, so this is the cluster plus the frozen variables. Okay, and so the cluster is going to be denoted by, so if T is my triangulation, then the cluster is denoted by x of t. Yeah, it's supposed to be somewhere here. And then right, so that's the cluster, and then the extended cluster is going to be x tilde of t. So once again, the extended cluster is you take the diagonals plus the sides of the polygon, which are the frozen variables. And so the theorem, well, I told you one claim, which is that I can express any diagonal in terms of the cluster. Well, this is supposed to be extended cluster, right? Because I'm also using the sides of the polygon. Oh, there is a question. Are the frozen variables an analog to the ones on the top and the bottom of the frieze pattern? Yes. Yeah, that's exactly right. Yeah, thank you. Yeah, soon I'm gonna explain exactly, like in each case, what are the frozen variables. They are invisible for the sum is 4 sequence, but I'm gonna make them visible. Anyway, let me state the theorem. Theorem, which is that any Pij, well, you can write it in terms of the extended cluster using the Ptolemy's theorem. And the claim is that any Pij is a Laurent polynomial in the extended cluster with positive integer coefficients. Okay? So in other words, I mean, it's a non-trivial statement, which is basically just planar Euclidean geometry. So you have 1, 2, 3, 4, 5, and you want to write P, let's say 2, 4, in terms of these, like P1, 3, P3, 5, and then the frozen variables. As frozens. And you have to do 2 flips, right? You have to flip this guy into this guy, and then yeah, so the flips are gonna, first you flip this diagonal, and then you do this flip, and then this is your 2, 4. And so as you keep, so you're going to have to do a bunch of flips, and when you do these flips, you're going to have to divide by some non-trivial polynomial, so the same kind of cancellation is going to appear. And the denominator is always going to cancel out, except for a monomial, and then the result is going to be a positive Laurent polynomial. Okay, any questions so far? Okay, now let me come back to the frieze pattern, because there is one more non-trivial thing going on. Back to frieze patterns. So let's say I take a frieze pattern. Okay. And let's say I'm gonna label all of these. So let's say I label this guy, or let's say F. Let's say this is F1, 2, and then this is F2, 3, F3, 4, and etc. And this is going to be F1, 3, F2, 4, F3, 5, 3, 5, F4, 1, F5, 2. So as I, instead of writing 4, no, it's supposed to be the 7-gon. Okay, let me actually try to write this down. F3, 4, F4, 5, 5, 6, 6, 7, and then 7, 1, 1, 2, and etc. So it's just periodic. 3, 5, 4, 6, 5, 7, 6, 1, 7, 2, and etc. 1, 4, 2, 5. I hope it's clear what I'm doing. 3, 6, 4, 7, 5, 1, 6, 2, 7, 3. So I'm going to label every entry of a frieze pattern by Fij, 1, 6, 1, 7. And so the ones are going to be labeled by the sides of my polygon, right? So I'm always taking the n-gon, where n is the order of a frieze pattern. Can I actually, let me try it. 1, 5, 2, 6, 3, 7, 4, 1, 5, 2, 6, 3, 7, 4, 1, 6, 2, 7, 3, 1, 4, 2, etc. 1, 7, 2, 1, 3, 2, etc. So the claim, which is surprising, is that the Fij's satisfy the Ptolemy theorem. Right, so whatever, I don't know, let's say somebody give me 4 indices A less than B less than C less than D, and then I'm gonna, can you say it again? Okay, 1, 2, A is equal to 1, B is equal to 2, C is equal to 3, and D is equal to 5. So I'm supposed to have 1, 3 times 2, 5 is supposed to be equal to 1, 2 times 3, 5 plus 1, 5 times 2, 3. And then let me try to find them in the table here. 1, 3, yeah, this is hard. 1, 3 is equal to 1, and 2, 5 is, well, it's here, is equal to 3. By the way, I have this triangle, right, which is then the same as this triangle here. So this relation, so the glide reflection is just saying that Fij is equal to Fji. Right? For example, this F12 is equal to F21 here, and etc. So this labeling is kind of very nice in the sense that it captures the periodicity not only the periodicity but half periodicity of the frieze pattern. F24, and this is F42. Anyway, let me go back to computing the relation here. So F13 is equal to 1. F25 is equal to 3. And then F12 is equal to 1. F35 is equal to 2. 1 times 2. F15 is equal to 1. And F23 is equal to 1. So not only, well, it is easy to check that the diamond relations are just special cases of this relation. But what's non-trivial is that even if you don't take the indices to correspond to the diamond, then still somehow you get this Ptolemy theorem. And I'm going to explain this next time, but let me just stop here. If you have any questions, please let me know. Otherwise, I'm going to see you on Friday. Yeah? Yeah, right. So first of all, the fi plus 1, which are the size, are just all equal to 1. And then if you take the diamond, it looks like fij, fij plus 1, fi plus 1, j, and then fi plus 1, j plus 1. So as you do, like, this times this is going to be equal to the sum of these two products, basically, I think. No, yeah, one of the products is just going to be fi plus 1 times fjj plus 1. Yeah. And the other one is going to be, right, so the three terms in here are the product of these two guys is equal to the product of these two guys plus 1. Yeah. Which is kind of tricky, right? Because if I set the all sides to be equal to 1, then my polygon is already uniquely determined, right? But then somehow, if I only use these relations, then there is Catalan many like integer things satisfying these relations. Yeah. So I'm gonna explain this next time. Any other questions or comments? All right. If not, then I'm gonna see you all on Friday. Thanks for tuning in.